And happy hello. Welcome to Dustin's Rhetoric Dialogue, where hopefully you've tuned in, turned on, and forgotten all the things you think you know, and remembered exactly what we told you last time. We're broadcasting live, of course, right now from beautiful New Smyrna Beach, Florida, where we ask, and we encourage our listeners, followers, and readers of both our YouTube and our Facebook pages. I keep wanting to say MySpace. It's like MySpace. It's shocking. But we do encourage our listeners and followers and readers to send in questions and or comments. This would be statements, in other words, for topic conversations for these webcasts and the webcasts to follow. Remember, there are no stupid questions except for the ones that we fail to ask. If we're not at liberty to discuss what's on our minds, then what is the sense of having a mind to begin with? If you are following or have been following our series on YouTube and or Facebook, starting with time travel. It's an excellent video. I'd highly recommend it. This will be video number 5. This will be appropriately titled The Theory of Everything, I think. I like that one. This video in particular was inspired actually by a conversation that took place tonight with a karaoke buddy of mine as we discussed functional purpose on the drive home. Whatever that means. I don't know. I just thought it sounded really cool. Again, we encourage our listeners, followers, and readers to go ahead and send us questions, comments, and statements or topics about these webcasts, and in hopes of sharing or at least helping to shed some light on but a few of the endless mysteries of the universe and God. Today's date is January 7th. It is, wow, 2:30 in the morning. Absolutely imperative that I should ask you, or invite you rather, that if you find our broadcasts to be both challenging and educational, I would ask that you go ahead and click subscribe. That keyword, of course, is subscribe. Capital SUBSCRIBE. Subscribe to our YouTube channel, and our address is real simple, of course, DJS California. DJS California at Yahoo, DJS California at YouTube, and DJS California at Facebook. You can find me by looking up Dustin J. Sanders or Dustin Sanders. I think I'm the 6th one on the list for the general, or in the general search tab. And then, of course, you can help us to advertise on Facebook, like our links, downloads, and share them, etc. DJS California at yahoo.com. So here we go.
Climbing way up into the sky. Well, we'll see if this ride is really like mine.
The problem with these guys is you can't find them. Nobody knows who they are. Nobody's seen them. They don't know if they're real. They don't know if they exist. They don't know if they're spirits, if they're human, if they're unless you're Dustin Sanders. Yeah, right. Yeah, unless you're Dustin Sanders. Unless you're you, but you're the only one that can do that.
So we're going to be talking about the theory of everything. Hey, that's great. What is the theory of everything? I'll probably start by explaining what is the theory of everything. Who or what is the theory of everything? The theory of everything really is it's theoretical physics. It fully explains. Is this thing on yet? We're talking about theoretical physics, people. It fully explains and links together all known, supposedly, rather, I should say, all known physical phenomena. It's supposed to be able to give you a prediction, or a precise measurement of the outcome of any experiment that could ever be carried out. That's pretty far out and radical thing to say, because what we're talking about infinitesimal universes, we're talking about time and space, we're talking about eternity and infinity, something that goes on and on and on and never stops. So to be able to link, predict any outcome that could ever happen within any experiment, whether it be in physics or chemistry or mathematics or anything else, is what we are referring to when we say TOE, or the theory of everything. Many candidate theories of everything have been proposed by theoretical physicists during the, well, it had to have been the 20th century, but during the 20th century, the primary problem in producing the theory of everything, of course, is that we find that general relativity and quantum mechanics are so hard to unify. General relativity is known by Einstein's theory of energy equals mass times circumference squared, or mass times circumference squared is equals to energy. How we arrived, or what was produced by that, of course, is the energy in this case, whereas quantum physics or quantum mechanics takes everything down at the microscopic level. So we're talking about time and space, but we're talking about something that can be predicted, or something that can be calculated based on light speed at 186,000 miles per second versus quantum mechanics or quantum theory. Now we're taking everything down to the excuse me, the microscopic level. The problem with the microscopic level is, of course, you go to atoms, and then you have protons, neutrons, and electrons, and then you have particles and subparticles. So we're finding that the smaller we get, the bigger we are, because we get smaller and smaller and smaller. We're finding more and more and more. That, of course, is the purpose of Large Hadron Collider over But anyway, initially the theory of everything used to determine, basically an ironic connotation, so just a terminology given to trying to describe everything, or to put everything in a box. We have claims to try to introduce a term in technical literature. Again, those are just things that have been put out there. Mostly me trying to sound smart and stuff like that, but just don't remember. But they do include quantum mechanics, electromagnetism, and things like that. The list of unsolved problems in physics goes on and on and on when we're talking about the theory of everything. But here's what happens. We end up coming up with more theories about more theories. So we have the theory of everything, or the idea, the thought of theory of everything, and now we've proposed M theory, or string theory. That is a universe connected within a universe, connected within a universe, connected within a universe. Again, we're getting down to the microscopic level, where if you begin to study quantum mechanics, you get down to your atoms, protons, neutrons, electrons, particles, subparticles. So as you go up, you go down, you go down, you go up, vice versa, verse vice. You with me? Okay, good. Is this thing still on? Just check. Now then,
tell us how you feel about her. Tell us a story.
She calls me Luke, and I love her. Why? Because I want to, and so choose to, thereby.
Oh my God.
Do it again. She calls me Loop, and I love her. Why? Because I want to, and so choose to, thereby.
No, you gotta say what happened. What did she call you? You gotta say what happened.
She calls me Loop, and I love her. Why? Because I want to, and choose to, thereby. She calls me Loop, and I love her. Mean it. Picture her. She calls me Loop, and I love her. Why? Because I'm her space-time. And so I try.
And dude, she doesn't call you.
She does call me Luke though.
One time.
She called me Luke.
Oh my God.
She did call me Luke, dude.
Oh my God.
She calls me Luke, and I love her. Why? Because I want to, and therefore choose to.
He's stupid.
She calls me Luke,
yeah,
and I love her.
You're an idiot.
Oh my God.
What the fuck?
She calls me Luke.
Does she?
And I love her. Why?
She didn't even call me.
She called that. No, she called that.
She calls me Luke.
Facebook.
One time.
And
Oh my God.
I love her.
And no wonder she
calls
calls
me
me.
Luke, and I wonder why.
She doesn't even know.
Wonder. Wonder. I said wonder. He said wonder.
She calls me Luke, and I love her.
Hey, Ashley.
Because I'm her space-time, and so I try. Almost. Ah, forget about it. Sanders. Black holes are among the simplest objects in the universe. They are simpler than stars, much simpler than planets, and vastly simpler than human beings. Black holes are what is created when matter is compressed into a very small place. They are general relativity's most extreme prediction. They are commonly created from the depths of stars many times the size of our Sun, usually forming from the collapsed core of a supergiant star after it explodes. At the heart of a black hole is a singularity, an infinitesimal point in space where the pull of gravity is infinitely strong and space-time infinitely curved. At the singularity, space and time no longer exist as we know them. So what would happen if we traveled into one? To answer this question, let's look at a simple black hole, one with mass, but doesn't spin or have any electric charge. This animation shows our descent. At the lower left is a graph showing our trajectory. The green region is a safe zone, where our spacecraft orbit around the black hole is stable and we can still get out. The yellow region is a risky zone, where our orbit is unstable. Here a short burst of our maneuvering thrusters will send us either into the black hole or off into outer space. The orange region is a danger zone, where there are no possible orbits for a spacecraft, stable or unstable. To remain in orbit in this zone, we must constantly keep firing our rockets. The closer to the horizon we get, the more we must fire our rockets to keep from falling in. The red line is the horizon. From here there is no escape. At the bottom right of this animation is a clock, which records a time lapse until we arrive at the central singularity. The clock records our proper time, the time we experience, the time on our wristwatch. In this animation, the clock slows down, not because time is slowing down, because it is more interesting to run the film slower, nearer to the singularity, so we can see more clearly what happens. As we begin our approach, we can immediately see the distortion of light around the edges of the black hole. This is the gravity well bending light, lensing the light from the background stars into long circular arcs. The event horizon is depicted as a red grid. This marks the boundary beyond which nothing can escape, not even light. Notice that we can see both the north and the south poles of the black hole simultaneously. Since the black hole bends light around it, we can see all around and into the back of the black hole, while at the same time looking at the front. This horizon is called the Schwarzschild radius. About 3 Schwarzschild radii marks the location of the innermost stable orbit, the green area in our trajectory. Here, circular orbits are stable. Beyond, they are unstable. Any material rotating around this black hole finds its innermost edge here. Anything slightly closer falls into the black hole. As long as we remain in this region, we can still get out. At about 2 Schwarzschild radii, we reach the risky zone, an area of unstable orbit. Any slip up here, such as a small firing of our thrusters, would randomly send us either headlong into the black hole or flying away from it. Also in this region, we arrive at a very special location known as the photon sphere, the distance where light rays can remain in orbit. This is the closest to a black hole that anything can get and remain in one. For our rocket to stay here, our thrusters would have to expend an infinite amount of energy. As we fall through the horizon at 1 Schwarzschild radius, something quite unexpected happens. Instead of falling through the red grid that marks our horizon, it stands off ahead of us. The horizon splits into 2 distinct entities, the horizon and the anti-horizon. Light from both of them hit us as we pass. The true horizon becomes visible only after we have fallen through. The anti-horizon continues to remain ahead of us and we never fall through it. It is a common misconception that if you fall inside the horizon of a black hole, you'll be engulfed in blackness. What happens instead? The universe appears brighter and brighter as you approach the horizon, tending to infinite brightness at the horizon. By this time in our journey, however, none of us would be able to sense any of this. Once inside, space is falling faster than light, carrying us inexorably inward. Here, we are now at 0.8 Schwarzschild radii. As we fall into a typical sized black hole such as ours, the tidal forces are weak enough that we can fall deep inside the horizon before we are torn apart. The gravity at our feet is stronger than the gravity at our heads. We can feel this difference as a tidal force which pulls us apart vertically, but at the same time we are being crushed in the horizontal direction like a rubber band being pulled. Finally, as we approach the singularity and we look up one last time, we see the intense gravity of the black hole has concentrated the view of the outside universe into a thin band around our waist. The views above and below are dim and red-shifted, while the views around our waist is bright and blue-shifted. We never actually get to see the center of the black hole because all light is rushing towards it and none away from it. Sadly, we'll never reach our final destination of central singularity. Our journey ends just short of our goal. Approximately 1/10 of a second before we reach the singularity, we will be torn apart by the tidal forces. This happens regardless of the mass of the black hole. In all black holes of any size, our journey will end at roughly the same spot. We will never reach the point of infinite curvature where space and time as we know them will come to an end.
She calls me Loop, and I love her. She calls me Loop, and I love her. Why? Why? She calls me Loop. She calls me Loop, and I love her. Why? Why?
She did call him Loop once.
She calls me Loop, and I love her. Why?
Well, she called you that by accident.
Because I choose to.
Oh my
Thereby.
God. Get a hotel room, dude. Dude, get a hotel
try.
room. No doubt.
No thereby. Alright, make it count. She loves you, you handsome devil.
Mean it, dude. Look at you. You're hot as a firecracker.
She calls me Loop, and I love her. Why?
Why?
She calls me Loop, and I love her. Why? Why? Because I want to. And so choose to, thereby.
Okay. Alright, she's watching.
Now,
try it again. Yeah.
She calls me
she's
Loop,
watching,
and I love
bro.
her. Why? Because I want to, and choose to. And so
you're
choose
space
to,
time.
thereby. She calls me Loop,
Yeah,
and
space
I
time.
love her.
Tell
Why?
her space time.
Because you're her space time, and so you try. Say it.
Say it, dude. You're her space time, and so you try.
She calls me Loop, and I love her. Why? Because I want
Try it
to,
again, bro.
and
Try it
so
again.
choose to, thereby. She calls me Loop, and I
He
love
needs
her.
help,
Why?
dude. Look at him.
Because I want to, and so
Killing me,
choose
Smalls.
to, thereby.
Killing me, Smalls.
Killing these balls. He says he's killing these balls.
Sing it. Sing it.
She calls me Loop.
Oh, that's bad.
Wait, hold on. She calls me Loop. Hold on. Hold on. She calls me Loop.
Yeah.
She does call me Loop.
No, she did.
Yeah. She calls me Loop, and I love her. Why? Because I'm her space-time.
You're her space time. Okay, think about this. How does she actually make you feel? How does
She calls me Loop.
Loop
Yeah.
or Luke? What did you say? Which one?
Loop. Not Loop. dude.
Loop?
Loop.
And I wonder-
L-O-O-P. Why?
She
She calls me Loop, and I love her. Why? Because I want to, and I'm
You're
her
her
space
space
time.
time and you try. That's why.
And I
Tell her
try.
the real reason. You're her space time and you try. She can accept that.
She calls me Loop,
Nope.
and I love her.
Off key.
Why?
You probably do.
Because I'm her space time, and I try.
That's good. I like that. Space time is good.
And she calls me Loop,
This is not a boys'
And I love her.
bitch.
Why?
I can't sing the words.
because I'm her space time,
He said boys
and
to
I
men.
try.
He
She
said
cut
boys
look.
to men.
This is what happened. Okay.
Tell like it
She
is.
calls me Loop,
Yeah.
and I love her. Why? Because I'm her space time, and I try.
Come on.
It's that simple.
That's right.
Now do you get it? Interesting.